A spider web is not decoration. It is not just a home. It is not just a random pattern hanging between branches. A spider web is a machine, a silent structure built from silk, tension, geometry, and vibration. To a flying insect, it can look almost invisible. A few thin lines suspended in the air. Nothing dangerous, nothing alive, nothing that seems capable of making decisions. But that is the cover story. Because to the spider, the web is not empty. It is information. Every thread is part of the system. Every angle has purpose. Every sticky spiral is placed to hold prey. Every radial line can carry vibration back to the center. And every movement inside the web becomes a message. A fly does not simply hit a web. It enters an engineered trap. The impact travels through silk. The web shakes. The pattern changes. And somewhere in the darkness, the spider reads the signal. Not with screens, not with machines, not with language, but with legs, with touch, with vibration, with a body built to feel architecture. This is why spiders are so misunderstood. People think they are building webs. But many web-building spiders are doing something far more advanced. They are building hunting systems. A web can be a trap, a sensor, a communication network, a restraint device, a warning system, a launch platform. A silk architecture designed to turn empty air into a deadly structure. And the silk itself is not simple. Some silk is strong enough to hold the frame. Some is sticky enough to trap wings. Some is flexible enough to absorb impact. Some is used to wrap prey. Some protects eggs. Some becomes a lifeline. This is not just thread. This is biological engineering. So tonight, we are not just looking at spiders. We are opening the file on one of nature's most silent architects, a creature that does not chase like a wolf, does not strike like a hawk, does not roar like a predator. It waits inside a structure it built from its own body. And when something touches that structure, the trap begins to speak. This is not just a web. This is architecture built to kill. So today, we are not just looking at a spider. We are opening the file on one of nature's most advanced trap-building systems. A creature most people fear because of its legs, its silence, and the way it appears from shadows. But the real story is not just the spider. The real story is the structure it creates. A web is not random. It is not decoration. It is not simply a place to rest. It is a design, a biological structure built from silk, tension, geometry, and information. To understand spiders, we have to go deeper than fear, deeper than the web hanging in a corner, deeper than the insect caught in silk. Because what looks fragile can function like a trap. What looks empty can act like a sensor. And what looks like thread is actually one of the most important engineering materials in nature. The spider does not need machines. It does not need metal. It does not need tools. It builds with its own body. It turns liquid silk into structure. It turns structure into detection. And it turns detection into survival. So before we understand the web as a trap, we must first understand the material that makes it possible, the silk, the biological thread that becomes architecture. To understand spiders, we have to begin with the material. Not the legs, not the fangs, not the fear humans feel when a spider appears in the corner of a room. The real secret begins with silk, because spider silk is not just thread. It is not a random string pulled from the body. Spider silk is one of nature's most advanced biological materials, a material made inside the spider, released through spinnerets, and turned into structure. With silk, a spider can build, climb, escape, wrap prey, protect eggs, create shelters, and construct traps. That is why the web is only the surface story. The deeper truth is that spiders are using silk as survival technology. Humans build architecture with tools: wood, steel, concrete, glass, wires, machines. But spiders build with biology. They carry their construction system inside their own bodies. Inside the spider's abdomen are silk glands. At the end of the abdomen are spinnerets. From these spinnerets, liquid silk proteins are drawn out and become solid fibers. A fluid inside the body becomes a line in the outside world, and that line can become a bridge, a lifeline, a trap, a signal wire, or a protective chamber for eggs. This is the first hidden truth. Spider silk is not one material with one purpose. It is a toolkit. Some silk is strong and structural. Some silk is sticky and used for capturing prey. Some silk is soft and used for wrapping. Some silk protects eggs. Some silk becomes a safety line as the spider moves. Some silk becomes the frame of a web. Some silk carries vibration. This means the spider is not simply producing thread. It is producing different types of biological engineering material. Each one has a job. The spider does not need to understand material science in human language, but its body performs material science. It creates fibers that can hold tension, absorb force, stretch under impact, stick to prey, transmit vibration, and survive outside the body. That is extraordinary. Because a small spider can use silk to control a space much larger than itself. Without silk, the spider is limited to the reach of its legs. With silk, it can control the air between branches, the gap between plants, the corner of a room, the entrance to a burrow, the pathway where insects fly. Silk allows the spider to extend its influence into the environment. This is why web-building spiders are not passive hunters. They are not simply waiting because they are weak. They are waiting because they have already built the first part of the hunt. The web does work before the spider moves. It intercepts prey. It holds prey. It sends signals. It turns empty space into a controlled structure. That is the power of silk. It allows a spider to turn the environment into a weapon. But silk is not only used for prey capture. Even spiders that do not build classic prey-catching webs still use silk. A jumping spider may use silk as a safety line. A spider moving across a branch may leave a drag line behind. If it falls, the silk can save it. If it needs to return, the line becomes a root. Silk can also protect eggs. Female spiders often wrap eggs in silk sacs. These egg sacs are not decoration. They are protective architecture for the next generation. The same material that can trap prey can also protect life. That is the paradox of spider silk. It can be deadly, and it can be protective. It can hold a struggling insect, and it can shelter fragile eggs. It can build a trap, and it can build a nursery. The material itself is not good or evil. It is functional. The outcome depends on how the spider uses it. Now imagine a spider beginning to build. It has no ruler, no blueprint, no hands like humans, no metal tools, but it carries inherited building behavior. It moves, attaches silk, pulls, tests tension, crosses a line, adds another, changes direction, connects anchor points, and slowly a structure appears. This is architecture without drawings, engineering without conscious mathematics. The spider's body moves through a sequence shaped by evolution. Movement becomes geometry. Silk becomes structure. Structure becomes survival. This is why spider webs seem almost impossible when we look at them closely. At night, there may be empty space between branches. By morning, a web is suspended there. Delicate, ordered, functional, built by a small animal using material from its own body. This is not magic. It is biology. But it is biology functioning like engineering. The spider's silk must solve real physical problems. A web thread must be light enough to suspend in air, strong enough to hold tension, flexible enough not to snap immediately, sensitive enough to carry vibration, sticky enough, in some regions, to trap prey, and efficient enough that the spider does not waste too much energy making it. Silk is costly. It is made from proteins. The spider cannot waste it forever. That is why some spiders recycle silk by eating parts of old webs. A damaged or dusty web may lose effectiveness. A sticky spiral may become less useful. Wind, rain, prey, and debris can all damage the structure. So the spider may take down parts of the web and rebuild. This makes the web different from human architecture. Human buildings are usually designed to last. Spider webs are designed to function. If the web works, it catches prey. If it stops working, it may be repaired, recycled, or replaced. This is temporary architecture, rebuildable architecture, living architecture. And the most important point is this: silk allows the spider to modify the world. Most predators move through the environment as it already exists. A wolf runs through a forest. A hawk dives through the air. A shark swims through water. But a spider changes the environment before the prey arrives. It creates a structure. It sets a trap. It changes empty space into a hunting zone. This is what makes spiders so unique. They are not just predators. They are environmental engineers. They use silk to design the conditions of the hunt. A flying insect thinks it is moving through open air, but the spider has already edited that air. It has placed invisible lines there. It has stretched tension through the space. It has created a silent structure waiting for impact. The web begins as silk, but silk becomes architecture, and architecture becomes a trap. That is why this first chapter matters. Before we talk about deadly webs, before we talk about vibrations, before we talk about trapdoor spiders, net casting spiders, and strange hunting systems, we have to understand the foundation. Silk is the foundation. It is the spider's construction material. Its safety rope, its weapon, its sensor line, its nursery wall, its prey restraint, its survival technology. The spider may be small, but silk gives it reach. Silk gives it control. Silk gives it architecture. And once that architecture is arranged correctly, it becomes something far more dangerous than thread. It becomes a trap. Silk is the material. But material alone is not enough. A pile of silk does not catch prey. A loose thread in the wind does not become a trap by itself. To become dangerous, silk has to be arranged, connected, tensioned, supported, placed in the path of movement. This is where the spider becomes an architect. And the web becomes more than a web. It becomes a hunting structure. When humans see an orb web, we often see beauty, a circular pattern, delicate lines, dewdrops, symmetry, something almost artistic. But the spider did not build the web for beauty. It built it for control. The web is not decoration. It is a machine suspended in air, a machine made from silk, tension, geometry, and stickiness. The classic orb web is one of the clearest examples. It has different parts. The frame holds the structure in place. The radial lines spread from the center like spokes. The hub gives the spider a position. The sticky capture spiral forms the dangerous zone. The anchor points connect the entire system to branches, walls, stems, or other surfaces. Each part has a job. The frame supports. The radii transmit. The spiral captures. The hub organizes. The anchor points hold. This is the first secret of web architecture. The web is not one uniform object. It is a system of specialized zones. If the frame fails, the web collapses. If the radii fail, the spider loses structure and signal. If the sticky spiral fails, prey may escape. If tension is wrong, vibrations become weak. If the web is too visible, insects may avoid it. If the web is too weak, insects can break through. So the spider must balance many problems at once: strength, flexibility, visibility, stickiness, energy cost, prey capture, vibration transmission, and placement. A trap works only if it is placed where prey will pass. That is why location matters. A spider may build between branches, across insect flight paths, near vegetation, in corners, or near places where flying insects move. The spider is not simply hanging silk randomly. It is placing a trap in a zone of opportunity. A perfect web in the wrong place is wasted effort. A smaller web in the right place can become deadly. The hunt begins before the insect arrives. It begins when the spider chooses the location. Then comes the frame. The frame defines the space the web will control. It holds the structure open. It allows the rest of the web to exist. Then the spider places radial threads. These lines move from the outside toward the center. They look like spokes in a wheel, but they are not decorative. They are support lines, travel routes, and signal lines. When prey hits the web, vibration moves through the silk. The radial lines help carry that information back to the spider. So the web does not only catch prey, it reports prey. That is what makes the architecture so powerful. The spider is not waiting blindly. It is waiting inside a structure that can speak through vibration. Then comes the sticky capture spiral. This is where the trap becomes dangerous. The frame holds the web. The radii support and transmit. But the sticky spiral is designed to hold prey. A flying insect may not see it clearly. It enters the airspace. Its wing touches sticky silk. Then another thread catches a leg. Then the body twists. The web stretches. The insect struggles, and the trap begins working. The sticky spiral has to do something difficult. It must be adhesive enough to hold prey, but the web must still remain usable. It must stretch under impact, but not fail immediately. It must hold wings and legs, but not trap the spider in its own structure. This is why web design separates functions. Some threads are sticky, some are not. Some are roads for the spider. Some are capture lines for prey, some are structural. Some are temporary. Some are later removed or replaced during construction. This separation is advanced design. The web is selective. It traps the target while allowing the builder to move. Now imagine the prey's perspective. A fly moves through the air. The web is thin. The background is complex. Light changes. Leaves move. The silk may be difficult to see. To the fly, the space ahead appears open. Then suddenly, impact. The wing hits silk. The web stretches. The sticky spiral grips. The insect pulls. The more it struggles, the more vibration travels through the web. Now the web is not only holding the prey, it is announcing the prey. The spider feels the signal. The trap has activated. This is the second secret of web architecture. Struggle becomes information. The prey's attempt to escape tells the spider where it is. Every wing beat becomes a message. Every pull becomes a signal. The insect is not only physically trapped, it is broadcasting its location. This is why the web is so efficient. The spider does not have to chase blindly. The architecture guides the predator. The radial lines act like pathways. The spider can move toward the strongest signal. It can approach through non-sticky threads. The prey remains stuck in the capture spiral. The design gives the spider the advantage. But web architecture is full of trade-offs. If the web is too dense, it may use too much silk and become easier to see. If the web is too open, smaller insects may pass through. If the silk is too weak, prey may escape. If the silk is too stiff, it may break. If the web is too loose, signals may fade. If the web is too tight, impact may damage it. The spider has to build a structure that works well enough in the real world, not a perfect diagram. A real trap in wind, rain, leaves, light, and unpredictable prey movement. That is why real webs are not always perfectly symmetrical. They are adjusted to the environment. One side may be larger. One anchor may be stronger. One section may be repaired. The web reflects the space available. The spider builds with what the environment gives it. This is architecture in chaos. And yet, the result is functional. It spans space. It holds tension. It catches prey. It transmits vibration. It gives the spider roots. It turns air into a hunting surface. That is the hidden truth. A spider web is not just a net. It is a structure that changes the rules of movement. Outside the web, the insect flies freely. Inside the web, flight becomes weakness. Movement becomes capture. Struggle becomes signal. The prey's own behavior helps the spider. That is trap architecture at its highest level. The spider does not need to dominate the entire forest. It only needs to control a small piece of space, a gap between branches, a corner, a flight path, a narrow opening. And inside that space, the web becomes law. Everything that touches it must deal with the spider's design. This is why web-building spiders are not passive. Waiting inside a web is not doing nothing. The spider has already invested energy. It has built the machine. It has placed the structure. It has connected the signal lines. It has prepared the sticky zone. By the time prey arrives, most of the hunt is already complete. The impact is simply the trap turning on. This changes how we see spiders. They are not just small animals making silk patterns. They are architects of predation. They use geometry as a weapon. They use tension as a detector. They use stickiness as restraint. They use structure as strategy. And once the web is built, the next question becomes even deeper. How does the spider know what happened? How does it separate prey from wind? A leaf from a fly? A mate from danger? How does silk become information? A web is not silent. It only looks silent to us. To human eyes, a spider web may seem still. Thin lines hanging between branches, a fragile pattern in the air, almost empty. But to the spider, the web is alive with information. Every thread can move. Every pull can travel. Every impact can become a signal. Every vibration can carry meaning. This is the hidden layer most people never see. A spider web is not only a trap. It is a sensory system. It allows the spider to feel what happens beyond the reach of its body. Without the web, the spider can sense what touches its legs. With the web, the spider can sense what touches the space around it. Silk extends awareness across the gap, across the air where insects fly. A fly hitting one side of the web is not just caught, it is announced. The moment the insect strikes silk, vibration begins. The thread moves, the tension changes. The signal travels across the structure, through the sticky spiral, into the radial lines, toward the hub, or toward the hidden retreat where the spider waits. And the spider receives that information through its legs, not as words, not as images, but as movement, pressure, tension, vibration. The spider reads the web by touch. That is why this chapter is called The Web That Feels. Because from the spider's perspective, the web is not only something it built, it is something it listens through. Imagine standing in a dark room. You cannot see everything around you, but every wall and every string in that room is connected to your fingers. If something touches one side, you feel the pull. If something struggles, you feel the pattern. If wind moves the structure, you feel the difference. That is closer to how a web works for the spider. The spider does not need to visually inspect every thread. It can wait, touching silk, legs positioned on lines, body still. Every contact point becomes a channel. The web brings the outside world to the spider. This is one of the most extraordinary parts of spider biology. They build a trap, then use that trap like an external sense organ. A trap without information would be incomplete. If prey is caught, but the spider does not know where it is, the trap is inefficient. If a leaf hits the web and the spider reacts like it is prey, energy is wasted. If wind shakes the web and the spider attacks every time, the system fails. So the spider must interpret. Is this prey? Is this wind? Is this debris? Is this a mate? Is this danger? The web provides the signal. The spider gives it meaning. This is not human intelligence. The spider is not thinking in full sentences. But its body is built to respond to vibration patterns. Through its legs and sensory structures, it detects tiny changes in tension and movement. The web carries the physics. The spider converts physics into behavior. That is biological intelligence. Not intelligence as conversation, but intelligence as response, a body tuned to a structure it created. Now think about the radial threads in an orb web. They connect the outer web to the center. When prey hits the sticky spiral, the signal travels inward. The spider can place its legs on different lines and feel differences in timing, strength, and direction. The web becomes a map. The trapped prey is not just somewhere. It creates a vibration pattern. That pattern guides the spider. This is why geometry matters. A web is not only built to hold prey, it is built to transmit information. If the tension is wrong, vibration may weaken. If lines are damaged, signals may distort. If the web is too loose, the struggle may not transmit clearly. If it is too tight, the structure may break. So the web must balance capture and communication. Stickiness holds prey. Tension carries information. Geometry organizes the signal. Architecture becomes sensing. Now imagine a fly trapped near the edge. It beats its wings. The sticky silk grips. The web stretches. The vibrations travel. The spider feels a sequence. Impact. Struggle. Pause. Struggle again. Line movement. Tension shift. The spider may move toward the strongest signal, but it may also hesitate, because not everything caught in a web is safe. A small fly is one thing. A wasp is another. A large beetle can be dangerous. A predator may touch the web. A falling leaf may create noise. So the spider has to judge the signal before fully committing. This is where the web becomes more than an alarm. It becomes an information filter. Wind moves the whole web differently. A leaf may hit and stop. Rain creates many small impacts. Prey creates repeated, localized struggle. A mate may create a special vibration pattern. The spider's survival depends on reading these differences. Move too late, and prey escapes. Move too quickly toward danger, and the spider may be injured. Ignore the wrong signal, and food is lost. So the web is full of decisions, not conscious human decisions, but biological response decisions. Approach, ignore, retreat, wrap, bite, wait, test, repair. Some spiders even use signal lines. Instead of waiting in the center of the web, they hide nearby. a retreat in a curled leaf, a dark corner, a small shelter. But they remain connected by a silk line. If prey hits the web, vibration travels through the line. The spider feels it from hiding. This is brilliant. The spider can stay concealed while still monitoring the trap. To the prey, the web may look empty, but the spider is connected. The trap is being watched through silk. This changes the feeling of the web. It is not just a visible net. It can be a hidden communication system between prey and predator. The prey struggles in one place. The spider waits in another. Silk connects them. The message travels. The spider emerges. And the web becomes alive. The darkest part is this. The prey's own struggle makes the signal stronger. A trapped insect cannot struggle silently. Every wing beat says, "I am here." Every pull says, "I am still alive." Every vibration says, "Come now." The web converts panic into information. That is what makes web predation so efficient. The prey is not only held, it is located. It is tracked through its own attempts to escape. The trap turns resistance into a message. But webs are not only used for prey. Vibrations can also carry communication between spiders. In courtship, this can be critical. A male approaching a female's web may be in danger. If he moves like prey, he may be attacked. So he may use careful vibration patterns. The web becomes a communication channel. A wrong signal can be fatal. A correct signal can allow approach. Again, silk becomes language, not spoken language, vibrational language. This makes the web even more complex. It can detect prey, warn of danger, carry mate signals, report environmental disturbance, and guide movement. A single structure becomes trap, sensor, and communication network. That is why calling it a web almost feels too simple. It is an external nervous system made from silk and tension, not literally alive by itself, but connected to a living body that can read it. The web feels through the spider, and the spider feels through the web. Together, they form a larger sensory system than the spider alone. This is a key hidden truth. Nature often hides intelligence inside systems, not only inside brains, but inside the relationship between body, material, and environment. For spiders, silk is material. The web is architecture. Tension is physics. Vibration is information. Legs are receivers. Behavior is response. Put them together, and a small animal controls a large, invisible space. That is the web that feels. Now, once we understand this, a web in a corner becomes different. It is not just dust and thread. It is a sensory architecture, a tension network, a structure that reports movement to a hidden predator. A fly does not simply collide with silk. It enters a system that listens. And when it struggles, the web speaks. But orb webs are only one version of spider design. Across nature, spiders have built many different trap systems. Some hide behind silk-lined doors. Some build funnels. Some cast nets. Some use silk like tripwires. Some launch themselves using tension. Some do not build prey-catching webs at all. So to understand spiders fully, we have to go beyond the classic web, beyond the circle, beyond the dew-covered pattern. Because spiders are not one kind of architect. They are an entire class of trap designers. The orb web is famous. It is beautiful, recognizable, almost symbolic. When most people think of spiders, they imagine a spider waiting at the center of a circular web. But that is only one version of the story. The deeper truth is that spiders are not one type of hunter. They are an entire world of trap designers. Some build orb webs. Some build sheets. Some build funnels. Some build messy cobwebs. Some hide behind trapdoors. Some cast nets. Some throw sticky lines. Some use silk like tripwires. Some hunt without prey-catching webs at all. This is why spiders are so fascinating. Their bodies share the same basic identity. 8 legs, fangs, silk, predatory behavior, but their hunting systems can be completely different. The web is not one invention. It is a family of designs, a collection of strategies built from silk, patience, vibration, and ambush. Let's begin with the classic orb weaver. The orb weaver builds a circular aerial trap, frame lines, radial lines, sticky spiral, a structure placed where flying insects are likely to pass. The orb web is a trap for the air. It converts flight into capture. But another spider may use silk differently. A funnel web builder creates a sheet of silk that narrows into a funnel-like retreat. The spider hides inside the funnel. When prey walks across the sheet, vibrations travel through the silk. The spider rushes out. This is not the same as an orb web. It is more like a silk alarm carpet connected to a hidden tunnel. The prey does not have to fly. It only has to step onto the wrong surface. Then there are sheet web spiders. Their webs can look like flat silk platforms. Prey may fall, stumble, or become tangled in the structure. Again, the design is different. The goal is still control. Control movement, detect vibration, create advantage. Then we have cobweb spiders. Their webs often look messy to human eyes, but messy does not mean useless. A tangled web can be extremely effective. Threads placed in different directions can confuse, trip, hold, and signal. Some cobwebs use sticky gumfoot lines that attach to the ground or surfaces. When prey touches them, the line can snap upward or hold the prey in tension. What looks like disorder may still be functional design. This is important. Humans often mistake clean symmetry for intelligence, but nature does not need symmetry to create function. A messy trap can still be a deadly trap. Then come trapdoor spiders. These are some of the most dramatic spider architects. They do not build an aerial web. They build a burrow, a hidden chamber in the ground. The entrance may be covered by a camouflage door made from soil, silk, and plant material. The spider waits inside, hidden, still, connected to the outside world through vibration. When prey walks near the entrance, the spider senses movement, bursts out, grabs the prey, and pulls it back into the burrow. This is architecture as ambush, not a web in the air, a hidden door in the earth. The trap is not meant to catch flying insects. It is meant to hide the predator until the final second. The spider becomes part of the ground. The door becomes camouflage. The silk becomes reinforcement. The burrow becomes the hunting system. This shows how flexible spider silk can be. It does not always become a web. It can become lining, a hinge, a door covering, a signal connection, a shelter wall. Silk is not just for traps suspended in air. It can become underground architecture. Now consider net casting spiders. These spiders use silk in a completely different way. Instead of waiting inside a large fixed web, they hold a small web like a net. They stretch it between their legs. They wait for prey. Then they cast the net over the target. This is active trap use. The spider is not just sitting in a structure. It is holding the trap like a tool. The web becomes a weapon in motion. The spider's body and silk act together in the final attack. This changes the idea of a spider web again. A web can be fixed or handheld. A trap can wait or be thrown. Silk can be architecture or a capture net. Then there are bolas spiders. Some bolas spiders use a sticky silk line with a droplet at the end. Instead of building a full web, the spider swings or positions this sticky line to capture moths. In some cases, chemical deception is involved, with the spider exploiting moth attraction systems. This is not a classic web. It is a hunting lure and sticky weapon. One thread can replace an entire web. Again, the principle is the same. Silk becomes strategy. The spider does not need the same design every time. It only needs a design that works for its prey. Some spiders use silk trip lines. A burrow or retreat may be connected to the outside by thin threads. When prey touches the threads, vibrations alert the spider. This is similar to a security system. The spider waits hidden. The thread reports movement. The predator responds. Silk becomes a warning wire. Other spiders hunt actively. Jumping spiders, for example, often rely heavily on vision and movement. They do not depend on large prey-catching webs in the same way, but they still use silk. A jumping spider may attach a drag line before leaping. That silk becomes a safety line. If the jump fails or the spider falls, the line can help prevent disaster. So even when silk is not the trap, it is still part of survival. This is the bigger truth. Not all spiders build webs to catch prey, but all spiders are connected to silk. Silk is one of the defining tools of spider life. It can become trap, shelter, safety line, egg protection, signal system, ambush structure, or hunting weapon. This is why spiders have spread into so many ecological roles. They can hunt in forests, grasslands, deserts, homes, caves, burrows, gardens, wetlands, tree bark, leaf litter, corners, ceilings, Underground. Some dominate the air with orb webs. Some dominate surfaces with sheet webs. Some dominate burrows with hidden doors. Some dominate close-range hunting through speed and vision. Some dominate through camouflage. Some through vibration. Some through silk traps. The spider world is not one design. It is a library of hunting systems, and each system reveals a different solution to the same problem. How does a small predator capture prey without wasting too much energy or taking too much risk? The answer changes. Build an orb web. Hide in a funnel. Wait under a trapdoor. Cast a net. Use trip lines. Swing a sticky lure. Jump with a safety line. Wrap prey quickly. Build a retreat. Protect eggs. Each strategy is different, but silk connects them. This is what makes spiders so successful. They do not rely only on one method. They have evolved many ways to turn material into advantage. That is why the title of this episode matters. Spiders are not simply building webs. They are weaving architectural traps. And sometimes, those traps do not even look like webs. A burrow door is architecture. A funnel is architecture. A net is architecture. A signal line is architecture. A sheet is architecture. A cobweb is architecture. A silk-lined shelter is architecture. The spider's real power is not just the web you see. It is the ability to design survival structures from silk. Structures that control movement, hide the predator, detect prey, protect eggs, reduce risk, and turn the environment into a hunting system. Humans often fear spiders because of their appearance. But their deeper power is not in how they look. It is in what they build. They build with material from their own bodies. They build without hands. They build without tools. They build in darkness. They build across empty space. They build underground. They build in corners. They build in places prey will enter. And when the structure works, the spider does not need to chase like a wolf. It does not need to fly like a hawk. It does not need to run down prey like a big predator. It waits inside the system it created. This is a different kind of power. Quiet power. Structural power. A predator that wins by designing the battlefield before the fight begins. That is the hidden intelligence of spiders. Not human intelligence, not blueprints, not conscious engineering, but evolutionary design expressed through behavior. The spider builds because generations before it survived by building. The trap works because selection preserved the behaviors that worked. The silk exists because biology refined the material. The result is one of nature's most elegant predator systems. A small animal that can turn silk into architecture, architecture into information, information into movement, and movement into survival. So the next time you see a spider web, do not see only thread. See the frame, the tension, the sticky lines, the vibration network, the hidden predator, the engineering, the trap. And if you see a spider without a web, do not assume it has no architecture. It may carry silk as a safety line. It may hide in a silk-lined burrow. It may guard eggs inside a silk sack. It may be waiting near trip lines. It may be carrying a trap you cannot see. Because spiders are not just web builders. They are nature's trap designers. They do not simply occupy the world. They rebuild small parts of it. They turn space into structure, structure into sensing, sensing into capture, and capture into survival. That is why spiders are among the most misunderstood predators on Earth. Their webs are not decorations. Their silk is not simple thread. Their traps are not accidents. They are architectural systems built by evolution. Silent, precise, deadly, and almost invisible until it is too late. If you found this documentary insightful, make sure to subscribe to Nature Declassified and turn on the bell icon, because in every episode, we uncover the hidden systems behind nature. And if you enjoyed this story, share it with someone who still thinks nature is simple.